Hi, welcome to the new tutorial. Have you ever wondered, what is the most efficient way of placing identical actors in the level, like a dense forest, a crowd of spectators in the arena, or in this case, a belt of asteroids? Usually, several thousands of actors are enough to slow the engine down below an acceptable frame rate. Yet here, I got 35,000 of asteroids, each with its own individual rotation. Almost all of them are visible at once, casting shadows. In total, they have up to 3 million triangles drawn every frame. Yet everything is perfectly fluid. A common sense among 3D artists is that a higher number of polygons means the troubles with performance. In fact, pushing polygons onto the screen, known as rasterizing, is the fastest thing in the modern graphics pipeline. Next, in terms of cost, is reading textures. It's limited by bandwidth and the physical distance of computer's memory to the video card's memory. Shading takes even more time, as shader programs usually contain between 100 and 200 instructions. They need to be evaluated at least once for every pixel of the screen. Only then comes the real bottleneck, the graphics driver. The driver translates and checks every OpenGL and DirectX function call into the final command for the GPU. It's a slow, inefficient process, and given that it frequently runs on a single CPU core, it's even slower. While GPUs really escalated in performance in recent years, the CPUs got like 20% advantage over the models from 10 years ago when you compare a single core. In OpenGL and DirectX up to 11, every separate object or material may potentially require an action from the CPU, causing a halt in the pipeline. If we were able to draw all the vertices in a single call, we would unleash the raw power of the graphics card. To pack multiple meshes into a single efficient object, so let's compare your typical static mesh component to a single instance. Basically, static mesh components are heavy. Every single mesh you place on the level will contain a transform, a mesh, materials assigned to it, physics properties, collision properties, lighting properties. And when you render them, you will use at least one draw call per a movable static mesh. So to draw an individual static mesh, the GPU has to be told what material to use, what mesh to use, and then to draw. So in comparison, a single instance is very lightweight. An instance contains a transform, and that's it. All the other properties are common for the whole group, so the mesh, the material, they are all set once for all the instances, and the same goes for rendering. You basically set up an array of transforms that contains the positions and the rotations of instances, and the GPU can take all that and draw them at once in a single call. So why rendering separate objects is so slow? Well, the GPUs are crazy fast at rendering polygons, but they need to be fed with data by the comparatively slow CPU. OpenGL and DirectX up to 11 were designed in the way that they have a global state. The global state contains the information about the current material to use and the current set of vertices to use, only one at a time. So do you want to draw another mesh with a different material? The CPU will have to stop, change the properties, and issue a new command, a new draw call. So drawing 100 meshes looks like that. Apply the properties of the static mesh, set the material and draw 100 times. And the simple draw command is actually slow. A partial solution to this would be batching. So you combine pieces into a single big mesh. In fact, you really get only a few draw calls, but the culling hides the entire object. When you move the camera around, or when it has to fade out with distance, it will hide the entire object at once. And the weight of the meshes in terms of disk space is really huge. Basically, you have to store this whole information about the copies in a single mesh, and you can imagine that level of detail is really hard to work with. So yes, it's often worth it, but only for groups of nearby objects. Now comparing it to 100 instances, you just upload a whole array of 100 transforms, set the material, and draw in a single call. The Instanced Static Mesh is the feature that you will use for that in Unreal Engine 4. So it has one template for all copies, all the properties are common, but how does it work with level of detail when you have all the meshes combined into a single object? Well, it doesn't. That's why they introduced Hierarchical Instanced Static Meshes. It's basically the same, but it creates multiple groups of instances, one per a level of detail, then moves the instances from one group to another based on distance. Now, how do we proceed with setting up instances in Unreal Engine? So using instancing in Unreal requires us to create a blueprint. Blueprints in Unreal Engine are templates of objects. So when you create a blueprint, in the beginning you get nothing. It's an empty object. But what they also call the blueprint is the visual language of scripting. So instead of using C++, which is the main programming language of Unreal Engine, you can achieve roughly the same functionality with blueprints. The event begin play node, the whole concept is based on an execution flow. So the flow starts, for example, here on an begin play node, which will fire off when the game starts. And then you specify what is about to happen. For example, it will print a text of hello. When the game begins, it will print hello. And then the next thing can happen. It can also print hi. To apply any changes, you have to hit compile. Now we drop the object onto the level and hit play. It says hi and hello. Once again, please check the upper left corner. Hi, hello. Great. For a more detailed introduction into blueprints, I really recommend looking into the official channel of Unreal Engine. Now, how do we proceed with setting up instances? In the upper left corner, you can add components, for example, a cube or a sphere, and set them up from the beginning, like changing materials, and so on. In the same way, we create a component of Hierarchical Instanced Static Mesh. Initially, it is empty, so we have to specify the mesh to use. And then, after setting up the materials, which are okay by default for me, you need to add new instances. As you can see, it says 0 elements. So we add the first one. Great. Add the next one. Now, if you were to move an instance, like you usually do with your objects, you will move all instances at once. Because you are not moving the instance, you are moving the entire instancing group here. So what you need to do is reset this how it was before, then go to instances and transform it manually here. all the transforms of the instances are specified here, like the rotation and so on. Yeah, right. I can see the instances here in the editor. One has a strength scale set by me. Well, maybe I should reset this to 1. Great. Now, the blueprint way, which will be the much more common way, is to delete all these instances and create them in the blueprint. You could do it on begin play, but then you won't see any effect in the editor, only after you start the game. So, there is the construction script tab, and it's the blueprint that is called every time an object is constructed, that is dropped into a level or modified, or its variables are modified by any way. Every such time the construction script is updated. So, in the construction script, we can drag the instance static mesh here, get, and tell the script to add an instance. So the execution flow goes to this node, it's the only node for now. It will add an instance, and here we can specify a transformation to it. So we drag from this input, make transform, okay, and for example the location will be -100 and the initial rotation will be 30. Let us see what we got. It's here. So now another one, for example like that, but the new transformation will be -200, rotation 50. Compile. Okay, I forgot to attach the instance group to create the instance in. Now it works. Yeah, we got 2 instances. But the method will be really tedious to use. It's not a production method. So what we need to do is to get rid of this for now. So to automate the method a little bit, we'll create a for loop. It's a basic programming loop. Here you insert 0. And here you insert how many times, +1, do you want the function to be called. So for example 50, to create 50 instances. And the loop body is what happens with every loop. So every time we want to create an instance to the instance static mesh, make the transform. Now we have only 1 input node in the location, not 3. So we drag from here, make vector, and now we have 3, x, y, z. So this index is the current index of the loop, the current run. So 0, 1, 2, 3, up to 50. So I want to take this, multiply its value by, for example, 1 meter, 100 centimeters in x. So the first will be at 0, the second will be at 100, the third in 200, 300, and so on. It will happen with every run of the loop. And when it's completed, I want to print done. Just like that. Okay. You can see the flow happening here. And in the viewport, I got 50 instances, separated by 1 meter. So maybe this shouldn't be 1 meter. Maybe I would like to specify this value. In the Variables tab on the left, I click the plus to create a variable, a changing value that I can also change in the editor, and call it separation length, for example. It can be anything. And the variable type will be float. Floats are numbers with the decimal part also. I drag the value onto the variable, onto the graph, click get, and use this value instead of this hard-coded 100. Compile. Now they are separated by 0. But if I click the I here, near the variable, I will be able to change the value. So now the separation length is 0, and as I move around, it gets bigger. 5, 50, 300. Great. So by using these basic blocks and creating the value to be specified as the instance transform, you can create a function that will place your instances in any manner you want. So you can download the asset files from the link that is visible on the screen or in the description of the video, and there you will see my function that is creating the asteroid ring. It's called BP instancing asteroid ring. Looks like that. I have added multiple variables to it, like for example ring radius, which we can change to 32,000 or to 12,000. And there is instance count by width and instance count by length. So for example, we want to have 100 instances over the entire length, or 200, or 500. The function looks like that, but it's not everything. I even set the mesh to be used by the variable to be able to specify it in the editor. Then in the for loop I create the instances, and the transform is calculated in another function. The function also created by me, which looks like that, and you can look into it in the materials that you download. There is also a more simple way, but with a more manual work involved, to use instancing. It's the Foliage tool. The Foliage tool is obviously based around instancing, because otherwise it won't be efficient at all. So you can specify your meshes instead of grass or trees, and just paint them around with the Foliage tool. Instancing in Unreal Engine is working out of the box and quite automatically, but there are some things you have to watch out for. The first thing, which is not obvious at all, is that the scale of Hierarchical Instanced Static Mesh components and their parent actors has to always be 1.0. Always be 1. Non-unit scale will cause calling issues among with other issues. Now remember to add instances to a single instancing group instead of creating multiple instancing groups. It's a common mistake, but if you follow the method I shown here in the tutorial, you probably will avoid it. Now, avoid setting mobility to static. It's possible to take the instancing group and set it to static and even bake light into it, but you shouldn't be doing this really. Instances are a method of copying dynamic objects which don't have static properties that are individual. They are just free copies, keeping only the transform, and the rest is common. As you could see in the video before, my instances were also rotating, like that. And the way I did it was to enter the event graph, and in the event tick, which is equivalent to do it every frame, I increase the actor's local rotation by a specified angle, the rotation speed variable. It is also possible to change the transform of a single instance, but then you will lose all the performance of this method. Update instance transform, and here you can specify the final transform to be set on the given instance. So as you can see, here you specify the index, it is for a single instance, so you will also need a loop for that. But the thing to remember, if you still want to use this method, because for example you have only hundreds of instances and not several thousands like I got, then please remember to set mark render state dirty only on the last instance. So you update all the instances with this turned off and the last instance with this turned on. How to achieve it in the blueprint is shown again in the materials you can download. You can enter the blueprints folder, asteroid ring, go to the event graph, and this is this part called experimental, which sets the rotation of the individual asteroid. To get it working, you just take the execution flow from here and and place it here in the loop, like that. Compile and run. But I warn you that in this case it will be slow. Yep, it's slow. Now, how we can optimize even more, and it is very recommended in the workflow with instances. You should combine the meshes into bigger meshes first, then copy them with instancing. You're basically limiting the number of instances by that. So the method of creating bigger meshes from individual meshes was introduced only in the Unreal 4.14, the latest release now. And here you can click Convert Actors to Static Mesh. Then we can use this group in our instancing group instead of individual meshes. Another very important thing when using instancing will be to avoid physics. Basically, when you can disable physics. Because with this amount of objects, it's really a hard thing for the CPU even to set up the physics, not only to collide. So, when you're setting up the object, select the instance group, and in the collision tab, remember to disable generate overlap events. It has to be set to off to maximize performance. From the collision presets, choose no collision at all. Can the character step up on it? Nope, it can't. And that's it. You can also play with shadow casting. For example, if the instances are so far away that it doesn't matter, you can disable shadow casting at all. The obvious place to gain more performance is also to enter the settings of the static mesh we are using, our template, and change the screen size when different level of details show up. For example, when the screen size is 1, 0, I have the LOD 0, the most detailed one. But as I go from it further, when the screen size of the object is like 6% of the screen's height, then the LOD 1 kicks in, and when it's 1% of the screen size, the LOD 2 kicks in, and so on. You can really go far with just adjusting these numbers to achieve really the maximum performance you can. Now, as you play inside the editor, you can click Lit here, the viewing mode, and check level of detail coloration, mesh level of details. You can see as the Hierarchical Instanced Static Mesh works hard to move the instances between the groups. We should be measuring our performance level quite often. So in order to do this, we click on the left top corner, press Stat, Engine, Unit, and also Stat, Advanced Engine. Here we can see how much time it takes to render a frame in milliseconds. In my case it's 8.33 milliseconds now. And in the counters area you have static mesh triangles. You can also enable Stat Engine FPS, but it's not a good practice to measure in FPS because, for example, when you want to check how much of a hit on performance is some feature, then it doesn't mean anything that it takes you 15 FPS or 30 FPS, because it will mean that using this feature 4 times, or this kind of object placing it 4 times on the level, will leave you with 0 FPS. No, it certainly doesn't work like that. So we measure in milliseconds it takes to render a frame. If you want to target 120 FPS, then you have to render the scene in about 8 milliseconds. 60 FPS will require you to fit in 16 milliseconds, and 30 FPS in about 32 milliseconds. Okay, so we're done with them for the current video. We have learned how to set up instances, how to avoid common mistakes with them, and maximize performance. Should you have any questions, and you will have, please ask in the comments, and hopefully some nice discussion emerges from that. And in the next video, we will learn not how to copy a single mesh infinitely around, but how to randomize the meshes, how to randomize the instances. Obviously, we can't use too many meshes to make the randomization and the natural look of the instances, because we will lose the main advantage of the instancing system. So we will have to use different methods, shader-based methods for that. But it's the topic of another video, so thank you for today, and see you later.